Hi, and welcome back to Hacker101. In this session, we're going to be talking about a couple of my favorite vulnerability classes: SQL Injection, Command Injection, and Directory Traversal. Let's start with Directory Traversal. Essentially, it's a path injection attack, which occurs when paths are constructed using unsanitized user input. By manipulating the construction of the path, you're able to walk up the file system tree and control where files are read from or written to. As you may know, in most operating systems there are two special directories, dot and dot dot. The directory dot is always your current directory, and dot dot is always the parent directory. By combining path components like these, we can walk practically anywhere on the file system. Let's take a look at a vulnerable snippet of code. In this case, we take the get parameter file, append it to a path base, then read that file and echo it to the page. Aside from the trivial XSS, if we can control any file contents, what can go wrong with this simple line of code? Well, consider the URL on the screen. Each one of those instances of dot dot will walk up one directory, getting us quickly to the root of the file system, then to just read etc password. As you can see, even the most straightforward and trivial instances of these bugs are of critical import. Best case scenario, these bugs lead to an arbitrary file read. The worst lead to code execution or even privilege escalation. Additionally, database contents are often revealed when the application shares a host with its database. Permission should always be set so that the database files aren't readable by the web server, but that constraint doesn't always hold true in real life. Now, consider a document sharing site. If file reads can be vulnerable to directory traversal, what about uploads? When you send an HTTP multi-part file upload, your client passes the file name to the server for processing. What if we put a directory traversal payload in this file name? We may be able to arbitrarily write files on the server. Now let's talk about mitigation. Despite these bugs existing absolutely everywhere, they're really quite easy to mitigate. In terms of direct mitigation, you have two routes. Don't allow path separators at all, if users shouldn't be able to change where files are accessed, or strip instances of dot dot slash from incoming paths. That said, the indirect approach is much safer for so many reasons, and it's just don't allow users to control paths whatsoever. Generate a file name based on the hash of the data and the indicated extension, for instance. If users can't control it, it can't be exploited. Now we've come to one of my absolute favorite bugs, command injection, and I found it in more applications than I can count. Imagine this scenario. You're testing a security appliance with a web interface for administration. As part of this, you have access to a ping function where you provide a host name and you get to see the results. One thing you may notice immediately is this looks a whole lot like the output of a normal ping command on a Unix-like system. Maybe they're just running actual ping and directly passing the host name on the command line. Well, if that's the case, we could potentially run other commands. You try to ping the host name google.com /echo test, and you see that it just silently gives back an empty page. Any use of an ampersand or semicolon will do so. What about backticks? A quick reminder for those who don't spend much time at the shell. Backticks allow you to embed a subcommand whose output gets embedded into the original command line. For instance, ping backtick echo google.com will work just like ping google.com. So you try exactly that string and you see a ping output just like you'd expect. From here, you own the system. It may take some work, but you can use commands from here to tamper with or exfiltrate data. The fun part here is that this scenario isn't a hypothetical. In fact, this is a bug that I found in the Yogi Pico Pro security appliance on release day. You can see the full posting about the bug at the link on the screen, including a proof of concept that set a new root password and opened an SSH server. This was a brand new device, not something loaded down with legacy code, and sadly, this is by no means a rare case. As with most of these kinds of injection bugs, the safest route is just to never embed user data into a command line at all. If you must, use a function specifically for escaping shell commands, for instance, escape shell cmd in PHP. Do bear in mind, though, that this function doesn't prevent the use of spaces, so attackers may be able to add new arguments to a command, which can be enough to own a system in some cases. It may seem rare that this would come up, but user input ends up in command execution all the time. Oddly, this is really common in enterprise code. I once found command injection in 5 engagements in a row. It's not the norm, but it does happen. And now onto SQL injection. This is one bug you may already be familiar with, as it was everywhere for a long time. This hasn't really changed, only the attention given to them has changed. You may already know SQL to some degree or another. In fact, you may have even seen SQLi in the past. For the purposes of this session, there are only 3 types of queries we need to be concerned with: select to fetch data, update to change data, and insert to append new data. Applications typically build up SQL queries as strings, dispatch them to the database, then process the result set, if any. It's in the query building that the problems tend to begin. Going back to Little Bobby tables, let's look at some code that his name may actually trigger. With this code, we're building a query directly using user input. That makes it the perfect target for SQLi. So we put in Bobby's name, and we get the query on screen, composed of 3 distinct parts: a select, a drop, and a comment. This is really the most trivial case of SQLi, and the payload is pretty clear. The select happens, then the table gets dropped from the system. Mitigation of SQL injection is generally fairly easy, and you have a couple options. The first and most dangerous is ensuring that all input is properly quoted and run through the appropriate escaping function. Second, you can use parameterized queries. These allow you to let the DB connector library or the database itself handle escaping. This is super safe but can be limited. For instance, you can't do arbitrary sorting with this method. The final and safest option is to use an ORM. This is the likes of Active Record in Ruby or SQL Alchemy in Python. With an ORM, objects are directly mapped to the database, and you can interact with it like any other data structure. This completely negates the possibility of SQLi, barring misuse of the library or bugs therein. Now you may be thinking, if it's all as simple as escaping some strings or using parameterized queries or an ORM, why do SQLi bugs still exist everywhere? It's really all a question of volume. Most apps will perform a huge number of separate queries, and the chances of you getting that right if you're doing it manually in every case is slim to nil. If there's even a single bug, it's game over for your application. In terms of finding these as an attacker, select statements are the most commonly affected and the easiest to detect. The 2 payloads on screen, the OR 1 equals 1 and 0 equals 1, will be your best friend here. The former will generally return every row, and the latter will return no rows. If you simply throw these into inputs and look for overly large return sets, or even pages that never return due to getting bogged down with data, you'll quickly find and hone in on SQL injection. If you want to take it further than just detection, you're getting into the realm of exfiltration. For this, my favorite method is a simple union. For instance, take the query on screen. This takes some input as a filter and returns 3 columns of data. Knowing that we have 3 columns of return data, we can try a query like you see on the screen. This union will let you return some arbitrary data or even select data from other tables. Just make sure you match the number of columns or the query will fail. If you can't see the query, just keep adding additional values to the union select and you'll eventually hit on the right value. Before we move on from SQLi, let's talk about blind SQLi. We just talked about some simple cases of SQLi, but what's the blind part? Blind SQLi is when your data is inserted into a query, but you can't directly see the results. For instance, a login page containing SQLi might be blind, in that you get back only if the login has succeeded or failed. There are 2 types of blind SQLi: oracles, giving a binary result back, or truly blind, giving no differences in behavior whatsoever. The login page I mentioned is an example of an oracle. You get back a single bit of data for each query, pass or fail. Truly blind SQLi happens a little less frequently and is a pain to exploit, but it's still totally doable. A good example is of a logging system where web requests are dumped into the database as you interact with it. You'll never see the results of these queries, and any failures will not impact the functionality of the application. Oracles allow you to answer a question with a true or a false, meaning you can exfiltrate data 1 bit at a time. For instance, you could read the administrator password for a site bit by bit and reconstruct it. You generally write a script to do this rather than doing it purely by hand. Exploiting an oracle for exfiltration is pretty straightforward, albeit a pain. But what about exploiting truly blind SQLi? If we can't possibly see the results, how can we hope to get information out of it? Well, you can often make these into an oracle. We can't see the query or its results, but we can see a side effect, how long it takes to execute. By introducing a conditional delay, we can make this blind SQLi into an oracle. For instance, delay 10 seconds if it's a 1-bit, no delay if it's a 0-bit. Then we can exploit it just like any other blind SQLi. You just watch the request time. This brings us to something important though. Differences in DB engines can lead to dramatically different exploitation paths. For instance, MS SQL has wait for delay to slow down queries, but in MySQL you'd use the benchmark function to accomplish the same thing. Being able to identify which DB is in play is important for that. To that end, here are a couple useful tricks. I suggest pausing to read through this slide. And now let's go through a little bit of wrap-up. To review, directory traversal is where user input is used to build paths. This can lead to arbitrary file reads or writes. For exploitation, the important thing to remember here is that ... is always the parent directory. Command injection is where user input is injected into a command line for execution without proper sanitization. This can often allow complete system compromise. Remember that backticks, semicolons, pipes, and ampersands are all your friends with this. SQL injection is where user data is put into SQL queries and escaped. This can allow destruction or exfiltration of data. In rare cases, it can even allow file system access or code execution. Most of the time you can see the results of your queries. When you can't, you have blind SQLi. With blind SQLi, you can generally get data out 1 bit at a time. This tends to be slow, but it's still dangerous nonetheless. That wraps it up for this session. There was a lot of information here, so please go back through anything unclear. In any case, thanks for watching and happy breaking.